gases at the same time, are you going to laugh or cry first? Okay. Count them both. Why? Why? You have to calculate what? You need to find how fast the gas is by doing what? Calculating mass. How do you figure out the mass? Just from the molar mass, from the periodic table. So if you have a mole of each, or the same amount of each, this has a molar mass of about 44. This has a molar mass from the periodic table about 17. Which one's going to travel faster, ammonia or the laughing gas? Ammonia. So you actually, if I release them both, because of a lower mass, it's going to have a higher velocity. You're going to start crying first. And it's going to, a wave of crying will kind of go backwards. And then, once the laughing gas hits, the front row will be laughing. The back row is trying to kind of progress through like that. Now, how could this work practically? Let's say you shop at Forever 21, right? I've seen you there. So, you want to go and get your favorite cologne because you have somebody, say in the dorms or whatever, that you want to date. Okay? You have a target. Okay? You go in for your target, but you need a good cologne. But your nemesis is probably also going to have cologne. Okay? So when you get to Forever 21, you need your calculator, of course. Some paper and a pencil. You want to find out the molar mass of the main ingredient. Because the one with the lowest molar mass is going to reach your target first. And you'll get the first impression over your nemesis. You got that? Okay, try that this out. Lowest molar mass is going to travel faster. Okay. You're welcome, by the way. Are you going to invite me to your wedding? Yeah. Okay. All right, next. We ended here. Okay. And, as you might expect, we don't want to do any more derivations. You can look in the reader or the textbook, but I'm going to put a dot, dot, dot. It means stuff happens, derivation happens, and we derive the following. U squared bar, remember that from before, that's the mean square. And now I'm going to take the square root of it. Okay, the square root of u squared bar, I'll say more about this in a second, is equal to 3, the number 3, R, that's the ideal gas law constant right up above, temperature over capital M. We get a number 10 here, make sure you know what stuff is. This is the molar mass. This is called the root mean square velocity. Why does it have that name? Well, it's the square root, mean for average, and then square because it's u squared. The root mean square velocity, or URMS, okay? For short. That's not exactly the average velocity, but it's what we call the root mean square velocity. It's close to the average. Why is this formula interesting? Because knowing the gas and the temperature, we can calculate its average velocity, or its root mean square velocity. So that's very helpful for us. Let me show you this picture here. This is from your textbook, but something equivalent is also in the reader. On page 46 in the textbook, this is page 220. If we plot velocity versus the percent of molecules at that velocity, you're going to get a curve like this. It looks sort of like a bell curve. And so, but there's a little tail on the right side. That always happens. So the peak there, at the very peak, is what we call the mode velocity. That's the most common velocity at the peak. The average velocity, u bar, is slightly to the right, typically. So the average velocity, because of the tail that goes to the right, the average velocity is slightly to the right of the peak. Then we got the root mean square velocity is slightly to the right of that. Almost the average velocity, but it's a helpful, good approximation of it. and it comes up in a lot of formulas if you go into chemistry more later. So that's why we're interested in the root mean square velocity. It gives a good estimate of what's going on with the molecules. Okay, and I'll just put a couple post-its up if you want to see there. I have a velocity overview and something on root mean square velocity. Okay, let me say something about units. For this formula, and actually everything we've done so far except the ideal gas law, for everything we've done so far in Chapter 6, I would recommend using SI units. It's just easier. So I recommend using SI units for everything we've done in Chapter 6 except for the ideal gas law. It just makes life a little bit easier. Okay, and so this would be no different. And again, I'm going to cover a little more material before we do an example using this, but we will do an example soon enough so you can see how to do the math with all this. I just wanted to introduce all the concepts first. Okay, we're in section 8. Section 8, chapter 6. This is page 225 in the textbook and in the reader. Let's see what that is. 47. And by the way, in the reader, if you want to take a look, there are also ways to calculate the mode velocity and the mean velocity. Well, we're not going to use it in this class. I just put it so you can see it. This is on page 46. So there are ways to calculate the other velocities, but it just turns out that the root mean square velocity is turns out to be significant as you progress in chemistry. Okay. This is kind of other gas properties. Okay, related to the kinetic theory of gases. All right, a molecular speed, a pretty common one. If you do any calculation, you get a root mean square velocity. Somewhere around 1,500 meters per second is pretty normal. Could be less, definitely, but in the hundreds, if not the low thousands. So about 1,500 meters per second would be about 1 mile every second. So they're moving extremely fast. But that doesn't mean if you're smelly that people in New York are necessarily going to smell that, because remember, it moves in rapid random directions, rapid straight line random directions. Or I'll say more about that now. And this is, again, one of the bullets. Let's see which bullet this was of the kinetic theory of gases. This was number 2, bullet 2 of our 5 assumptions. Our random direction straight lines, we call that a random walk or a tortuous path. So it's going, it's bouncing off stuff, it's going all kinds of directions like that. Okay? Random walk, a tortuous path. And so thus when you have a lot of these here, they'll undergo something called diffusion. You must be my biggest fan. I totally understand. I'm surprised when I see me in the mirror. I'm like, oh my gosh. Sorry, I can't help myself. Vibration of particles. Okay, so diffusion is a migration of particles. That's kind of what we were talking about with that example. I release ammonia and N2O here, a laughing gas, and it spreads, it diffuses through the random walk outwards. Okay? So that's called migration. There's another way that the gas molecules move, and that's diffusion. Okay? This is an escape out of an orifice. So if we have a box and our gas is here and it's escaping out of a single point versus going any particular direction but coming out of a singular point, that's called diffusion. Diffusion. Okay, and we can actually have formulas for these. We do, and I'll show you right now. Let's take a look at the root mean square velocity. I Again, we can estimate the root mean square velocity of any gas. We just need the molar mass and the temperature. So let's say this is gas A. This is A. Okay? And then now, let me get a different color. Let's take a little ratio here. Let's do the root mean square velocity of gas B. Or B now. Okay, so do a little ratio here. Saying these two equal to each other. Like that. Okay, and now if I rewrite this below, we've got the root mean square velocity of A, the root mean square velocity of B. Okay, 3, it doesn't matter if it's with A or B, it's going to cancel. Is that okay? 3's gone. It's a constant. R is a constant. It doesn't matter if you're with A or B. The temperature of A and the temperature of B are going to be the same in the same context. So temperature is gone. Okay? The only difference is the molar mass of A is not going to be the same as the molar mass of B. So you're going to have 1 over the molar mass of A divided by the square root of 1 over the molar mass of B. Or if you know your algebra, the denominator flips up to the numerator. Specifically, this molar mass of B is going to flip up. So it would be the square root of the molar mass of B over the molar mass of A. Or rewritten again. This here, I'll circle this, box it, something, rectangle it. This is Graham's law. Oh, Graham's law. Okay, that's Graham's law. Where you can find the ratio of two velocities of A and B given the molar masses. Which, just by knowing the identity of the gas, you'll know the molar mass. This is primarily derived for diffusion, but it happens to also work for diffusion pretty well. So we're going to use it for either case in our class. And we can expand this quite a bit to say the following. In general, a property of gas A, and there are several properties this will work for, divided by a property of gas B is going to equal the inverse of the molar mass. What properties does this work for? Well, we just saw it works for the root mean square velocity of A over B. By the way, on the exam, this is what I'll give you, what's boxed up here for exam 2. But I'm going to tell you right now some additional properties it works for that you just need to remember. Okay? So what else does this work for? And this is kind of elaborated on page 47 of the reader. It also works for distance. Distance of A over distance of B. So how far something travels also is equal to this ratio. That I'll underline one more time, right there. That ratio is equal to any of these property ratios. What else? The amount. I'll put A and T for amount of A over amount of B. You'll see one of these on your extra, I believe the extra credit homework. And then also, one more, but this one's kind of funny. I'm not going to derive it. The time ratio. But notice something funny about the time ratio, where the first 3 are inverted compared to the molar mass. The last one is not inverted, it's the same. Okay? It'd be up for you to remember that, but this is an expanded version of Graham's law. Again, on the exam, I'm only going to give you these two. As far as the formula, you need to remember the rest. But it works for all 4 of these properties to the right. Velocity, distance, amount, and time. All right. Good with that? We're going to section 9. Again, one last section before we do examples. Just like we derive something for real gases, There's also information for ideal. We rated ideal. There's things for what's called real gases, which are gases that are not ideal. What does not ideal mean? Remember those 5 assumptions of the kinetic theory of gases? Whenever it breaks any one or more of those assumptions, it starts to become what we call a real gas. It's actually not necessarily just one or the other, it's a continuum. Something can become more real. So it's either ideal or, because it's starting to break an assumption, becoming more and more real of a gas, meaning less ideal. So it'd be sort of a continuum. For an ideal gas, we know the following. PV equals nRT. Oh, and again, if you need the page, it's page 48 of the reader, and for the textbook, page 228. Okay, and I'm going to rewrite this. PV over nRT equals the number 1. That number 1 is called the compressibility factor. Compressibility factor. For an ideal gas, that number is 1. For a non-ideal gas, it's not the number 1. It will vary, be less or greater than. So this is a measure of how non-ideal something is. How real is it? The more real it is, the more it varies from the number 1 when you divide these numbers. So I've had exam questions that say, here's the pressure, volume, moles, and temperature. Is it ideal? If you calculate this compressibility factor, get the number 1, it's ideal. If it's a number that's not close to number 1, it's not ideal. Yeah. Real and non-ideal. She's asking about real. What does that mean? Real and non-ideal will be synonyms. And that means that it's not ideal. And that means it's breaking one of the 5 assumptions of the kinetic theory of gases, which are, it takes up volume. There's no elastic collisions. They're attracted to each other. Things like that. Okay? So again, breaking one of the 5 assumptions of the ideal gas, of the kinetic theory of gases. Okay. So there's a couple of things listed on page 48 of the reader. So for example, you can have, if there's actually attraction towards each other, that'll change the pressure. And there could, if they're taking up volume, that'll change the volume a little bit. And so, where this is called the ideal gas law, or we also call it, I've used this word once before, EOS, equation of state. This is the equation of state for an ideal gas. You can also have an equation of state for a real gas. There's actually many equations of state. There's not just one for real gases, depending on how you want to approximate that real gas. And the one that your book teaches you, one of many, is called the van der Waals equation of state. The van der Waals equation of state for real gas, in contrast to the ideal gas law. Okay? So I'm going to write it down for you right now. This is the van der Waals equation of state. It's the A real gas law. Okay? There's many. It looks like this. It looks a little crazy the first time you see it. P plus n squared over A divided by V squared, V minus NV equals nRT. If you take a look at it, it looks a little bit like the ideal gas law. There's nRT, and here's the P, and here's the V. But you see this craziness here, that and that. You're like, what the heck are those things? Well, they have the same variables. There's n, there's v. You see a lowercase a and a lowercase v. Those are constants that would have to be given. But in either of these two cases here, these are corrections because of the variance from the ideal gas. This correction has to do with breaking the no attraction rule. So if gases are actually attracted to each other, it will change the pressure, and van der Waals corrected for that change in pressure by adding that term. The second term is a volume correction. And this is the breaking of the assumption the gases take no volume. They actually do take a volume, and van der Waals corrected by using that term there, where my pen is. Okay? So they're correction terms. And all real gas equations of state look something like this with corrections for the pressure, sometimes the volume, sometimes both. Lots of different possibilities. In your textbook, you have this table on page 228. Just wanted to show it to you. An ideal gas, remember that lowercase a and b? Let me show it to you again. This b right here and this a right there, that's in the van der Waals equation. And that's what this is, a and b. For ideal gas, a and b are 0, and the compressibility factor is 1. Okay, that's an ideal gas. But you can see they can vary depending on what gas you have. And in fact, no gas is truly ideal, but you can see like hydrogen and helium, pretty darn close to ideal. So I would, for our purposes, I would consider anything definitely, it's a continuum, but anything 0.9 and above is definitely for us in the ideal range. Once you start getting out of that, it starts to become a little less ideal. We might approximate it using the ideal gas law, just for out of ease, but it doesn't really fit the ideal gas law perfectly. So again, this is variance because they're breaking one of those 5 assumptions or multiple assumptions, and this is specifically for the van der Waals equation statement. If there was a question about this on an exam, I'd have to give you A and B in order to solve the problem. All right. Let's go back. This is page 42 of the reader. Let's see what we just did. We just did the whole left side here. With the kinetic theory, there's the 5 assumptions. We saw the kinetic energy, there's 2 formulas, 1/2 mv squared and 3/2 RT. We saw there's a quote derivation, we didn't do the whole thing with the ideal gas law. There's actually a derivation of the root mean square velocity, but there's other velocities too, the mode velocity and the mean velocity. And then there's Graham's law, which comes out of the root mean square velocity formula. So everything here was derived, though we skipped the derivation just because of our curriculum. But you can see more info about the derivation if you want to take a look at the textbook or reader. Okay, now, we did real gases too. Toss that in right there. Okay, the next section we're going to tackle is all this mess here, which is the gas laws. Okay? So this takes us back to section 2. But really, before that, I'd love to do an example of how you would do anything here. A lot of the kinetic theory is just purely conceptual, but some of it we can do calculations for. And here's a pretty typical calculation. And this will apply a lot of the formulas we were just looking at. We're going to do helium and methane here. Should know that methane is CH4. Okay, let's try this. So what's the ratio of diffusion rates, that's velocity, of helium and methane? What we're saying is, it's the root mean square velocity of helium to the root mean square velocity of methane, CH4. We want that ratio. Okay? So, this is Graham's law. Whenever you're talking about 2 compounds, talking about Graham's law. So that's the molar mass of CH4 divided by the molar mass of helium. In this case, because it's a ratio, just like the dilution formula, we don't really care about the units as long as we're consistent. So units are less of a factor here. The molar mass of CH4 is about 16. The molar mass of helium, and you can get more digits from the periodic table, is 4. So that's going to be the square root of 4. Basically going to be the number 2. Which one's faster, by the way? Helium or methane? Helium. How did you know that? Yeah, there's 2 ways you could have known that. Obviously, by looking at this number. But more conceptually, helium's smaller. So it should go faster. Specifically, it goes twice as fast. 2 times faster than methane. Okay. Now, let's do the next one. What's the root mean square velocity of helium at 0? Okay. So, now I'm just talking about one compound. So now I'm going to use this formula. One compound, I just use this formula. That's the square root of 3r. I need this r. Why? Because I want the one with SI units. T, 0, and I need SI units again, so I'm going to change it to Kelvin. And then divide this by M. Now from the periodic table, I get, if you look at the periodic table, it's 4.003. What's the problem? I can't use that number though. Why not? I have to do something to it. What units is it? Grams per mole, that's not SI units. What's SI units? Kilograms per mole. So I can't use 4.003. I need to divide it by 1,000 to change it to kilograms per mole. That's probably the most common mistake students make, is not putting this in kilograms per mole because this is SI units. Okay, so, and kilogram is an SI unit. This turns out to be 1304 meters per second. Okay. So you have 1304, that's a pretty expected number. I expect a number anywhere between 500 and 2,000, somewhere in that range typically. Okay. Now it wants us to do the corresponding velocity for methane. Let's do that. Three, R, same R. T, same T. Only thing that changes is the molar mass, which is 16.042 kilograms per mole. Again, I have to divide by 1,000. I just used a lot of digits here, kilograms per mole. So from the periodic table, just got to divide by 1,000 to change it to kilograms per mole, not grams per mole. I got 651. What's another way I could have found this number? Got it, yeah. This ratio, the ratio is 1 to 2. I could divide this number by 2. So that's another way I could have solved it. Just take this number, divide by 2 plus this ratio. All right, next. Oh, I think we'll have to save the last part for next time.